Bismillah Rahman Rahim. In this video, I am going to explain mean shift segmentation. Mean shift, in fact, is a technique for classification of data, but we can use mean shift to classify data into different segments. The segmentation done by mean shift segmentation will be based on some features, and we will group the data containing a certain feature into one class, whereas data containing some other feature will be grouped as another class. So a mean shift algorithm is a feature space technique that locates maxima of a feature density function. But this line has different new words or some things that needs explanation. I'm going to explain these things by answering three questions. The first one is, what is a feature? A feature is something unique in an object. For example, what are your facial features? Your facial features are only specific or are unique to you. An other person or any other human being will have some other facial features. So using those features, we can identify different human beings differently. For example, your friends and your relatives, their brain have already learn the features present on your face. So whenever they are going to see you, they will recognize you. Or I can give another example of, for example, any car. A car has certain features in it. A car of one brand will have some features, whereas a car of another brand will have another feature in them. Or same brand cars can have different features. For example, all other features will be same if you talk about a certain model of a car, or other features will be same, but maybe both cars have different colors. So you can easily identify by looking at the color feature of the car that which car belongs to you and which car doesn't. Or if they have, for example, same color, then they must have a different license plate feature. So the numbers or the alphabets appearing in the license plate of those cars, they will act as features and they will help you recognize which car is yours. So I hope that you understand that what is a feature. Now, what is a feature space? Just like a simple Cartesian graph in which we have, for example, an x and y axis, this x will represent something, whereas this y will represent some other quantity. But what if this x is representing some feature and y is also representing some other feature? For example, we are talking about squares and circles only. There are different sized squares and circles, and the feature which we are looking at are, for example, the circularity. So this x might be representing circularity, whereas y might be representing the radius or the maximum dimension. Maximum dimension. So if we want to classify these five objects using a feature space, how can we do it? We will go to this first object, we will measure its maximum dimension, and we will also measure its circularity. Maximum dimension would be the diagonal in case of squares, and circularity has a specific formula which is out of scope of this lecture, so I'm going to skip it. I hope that you know that what is this formula of the circularity, or you can easily figure that out, search it out on your own. Anyhow, circularity for the square is going to be somewhere around 0, whereas it is going to be somewhere around 1 for circles. So if we talk about this object, this first square, what is going to happen? We are going to measure its maximum dimension and circularity. Most probably it is going to lie somewhere over here. So it has a large maximum dimension but a low value of circularity. Same will be done for this square. So it might lie somewhere over here. It has a smaller maximum dimension and a smaller value of circularity. And for this square, it might lie somewhere over here. So these are three dots which are representing these three squares in feature space. And what about these circles? If we measure maximum dimension of this circle and the circularity of this one, it might come somewhere over here. So it will have a smaller maximum dimension but a large circularity value. And what about this circle? It will have a dot somewhere over here. So you can see that this feature space has divided these objects, circles and squares, into two different objects in the feature space. What if you get a new unknown object? What you need to do? You need to measure the maximum dimension of it and the circularity of it, and you need to plot its point somewhere on this feature space. So for example, the new object which you got corresponded to this dot somewhere over here. So by looking at the distribution of data in this feature space, logically you will conclude that points lying in this region will correspond to a circle, whereas points lying in this region will correspond to non-circular things or squares. So if this unknown object is somewhere over here, then most probably your system will categorize this new unknown object as a circle. So I hope that you get an idea that what is a feature space. So this is a feature space where these x's are representing some feature values instead of some time or some voltage value or some amplitude. These x's are representing some feature values. These features values, they can range from 1 to millions. So a feature space can be as simple as one dimensional feature space or as complex as millions dimension feature space. So the third question is, what is feature density function? This density function is going to somehow mathematically model the density of feature points lying in the feature space. For example, what is the density of features in this area? And what is the density of features in this area? Somehow this feature density function is going to express this information mathematically so that it can be used for analysis and for categorization. So consider a very simple 1D example. Consider a set of points in a one-dimensional feature space. So we have only one axis because we only have one feature. We had 10 different objects and we calculated that feature value for all those 10 objects. And we plotted those points somewhere on the feature axis. So, for example, this feature value was the height of students in the class. So these 10 points are representing heights of 10 different students in the class. So you can see that 5 students, they have a little bit shorter length, whereas 5 students are who are taller. Your brain can easily categorize these 10 points into two categories. But how we can do this thing mathematically or through some computer software? So we want to generate two groups corresponding to two parts of feature space. That is, each group will have a certain feature value in it, and we want to locate areas of high density of points. That is, you can see that over here, this is the area where there was a high density of points, whereas this is another area where we have a high density of points. We have no values in this region and no values or feature values in this region and in this region. So this thing can be captured using a kernel density estimation function. Now what is a kernel density estimation? So once we have used this kernel density estimation, we will group this data into two groups like these red and green dots. But how can we do this thing? How can we convert our discrete set of points into a continuous function that will give us some higher value of feature in one region and a lower value of feature in another region? So we need something like this. We know that in this region we have a high density of feature values, more number of objects were lying in this region, and we have this region in which another set of objects were lying. So this function is a continuous function which has a higher value in these two regions, whereas it has lower values in other regions. So how we can generate this kind of function? And later on, I'm going to describe how we can use this function to classify these data points. So for this thing, consider a kernel function k of x having this form. It is nothing but a bell-shaped Gaussian curve. It can be something else as well, but for simplicity, we are going to discuss only this kind of kernel function, which is a bell-shaped Gaussian curve. This kernel function is representing that the probability that a feature value will lie somewhere over here is maximum, whereas probability that this feature value can lie somewhere in this region or this region is mediocre, whereas probability that feature value will lie somewhere over here is quite low. So how we can use this kernel function to get our continuous function? It's very simple. Simply apply this kernel function onto each data point. What is happening over here now? Now, the application of kernel function onto this data point is showing that this point will have the maximum probability of lying over here, whereas it may lie somewhere over here, over here, over here, or over here. But the point lying over here has minimum probability or negligible probability. So application of this kernel function onto all 5 points over here will look like something this, and application of this kernel function on all 5 points over here will look like this. Now the next step is again a simple one, which is to sum up the values of these kernel functions. So what is going to happen when we'll sum these functions up? Over here you can see that there is only a one function. Let me remove these things so that it becomes clear. So over here you can see that there is only one function. So the value of this function will be the only value over here. Over here there is only again one function, but in this region you can see that these values are going to add up. So the function value is going to increase. In this region, these values are going to add up. And in this region, these values are going to add up. So at the end, we are going to have something like this. And same is going to happen over here. We are going to have something like this. So now this blue line is going to correspond to a continuous function which we desired. So over here you can see that we are getting two peaks, and each peak will represent one mode of data. For example, this is one peak and this is another peak. So if an unknown object is somewhere near this peak, this one, then it will correspond to this group, whereas if that unknown object is near this peak, then it is going to represent this group. So to which peak will this point correspond? To find out this thing, you need to move this point in the direction of the gradient of green curve. For example, over here, the direction of the green curve is negative. So you need to move this point in the negative direction. So this point will move in this direction. This point will also move in this direction because over here, this green curve has a negative gradient. Whereas this point might not move because over here the gradient is 0. This point will move in a positive direction because gradient over here is positive. This point will also move in a positive direction because gradient over here is once again positive. So what is going to happen after some iterations, all these 5 points, they are going to group up. They are going to get to one point, that is this peak. It is just like climbing a hill. So it is a hill and the person standing on this side, they are climbing the hill from this direction, whereas a person standing over here, he's climbing the hill from this direction, and at the end they both will reach this apex. Same thing is going to happen over here. These points, they are going to move in positive direction like this, and these points are going to move in negative direction because the gradient of the curve over here is negative. So they are going to move in this direction. So at the end, after some iteration, all these 5 points will come over here, and in one dimension they are going to come over here. So all points will be corresponding to this peak. So at the end we are going to have only 2 points, this one and this one. So these 2 points, they are going to correspond to modes of the PDF or the probability density function. So this thing is going to act as cluster 1. This is first cluster. So it is cluster 1 and this is a second cluster. So we have two different categories in which we can divide all our data points. I hope that I have explained this concept quite clearly, but if you have any questions, kindly do ask through comments or through some other means of communication. Before moving on, I'm going to discuss two problems associated with kernel density function. I've chosen a kernel density function of a certain standard deviation. But what if I've chosen a kernel density function of a small bandwidth or of a small standard deviation? For example, I might have chosen this kernel function. When I'll apply this kernel function onto these points, I'm going to get these peaks, and when I'm going to sum them up, I'm going to get this green curve. Now you can see that there are multiple peaks present. That is, for every point there is a peak. So there will be no movement of these points because this, for example, this point is already at a zero gradient. It is at a peak. This point is also already at a peak, and this point is also at a peak. So using a small bandwidth will create large number of modes, which is quite undesirable. So you'll have to choose a bit larger standard deviation or a bandwidth. But what if we choose a large bandwidth? Then what is going to happen? This is what is going to happen. All these points are going to mix up. A kernel function applied to this point will be something like this. It is going to overlap with kernel functions of all other points so that when you sum up these kernel functions, you are going to get only one peak. So now you only have one mode. This kernel function has categorized our data into one category only. So all these points are going to correspond to one peak only. So this is the problem associated with choosing a wrong value of bandwidth for kernel function. So you have to choose an optimum value so that you get the desired amount of modes or the desired amount of categories. So what is going to happen? We will, if we have chosen correct value of bandwidth, we are going to move each point in the direction of the gradient, and we will see that at what peak that point is approaching. Whatever peak that point is approaching, we will assign that mode to that particular data point. So at the end, all these 5 points are going to gather over here, and all these 5 points are going to gather over here, and they are going to stop them. So we have achieved stability with 2 points. So we will call this one mode 1 and this one mode 2. So these 5 points will be assigned mode 2 or category 2, and these 5 points will be assigned mode 1 or category 1. I hope you have understood that how these data points are being categorized into different categories. This example was quite a simple one, that is, we only used a one-dimensional feature space. In the next slide, I'm going to discuss an example which involves two-dimensional feature space. So how this mean segmentation is going to happen over there. So consider this 2D example whose feature space is given like this. So this y-axis, it is representing some feature value. I'm going to label it as feature 1, and this x-axis is representing another feature value. I'm going to label this thing as feature 2. So we have different objects, maybe around 50, and for each object we calculated these two feature values. These two features, they can be, for example, height and weight of students, or they can be, if we are talking about some objects, they can be the area and the perimeter, or the circularity and rectangularity, or weight and maximum dimension. You can use, depending on the application, these two features, they can correspond to anything. So once you have calculated these two feature values for all the objects, what you need to do, you need to plot these points in a feature space. So in this case, we are having a two-dimensional feature space, and we have plotted all these red points over here. The next step would be to apply a kernel function. In one-dimensional feature space, we needed a one-dimensional kernel function. But in a two-dimensional feature space, we will be needing a two-dimensional kernel feature. So a two-dimensional kernel function will have two dimensions in it, and it will have lower values over here and higher values as we move towards the center. So it will look like a bell if you look from the top. So we need to apply this kernel function to all these points and then sum up all the kernel functions. So what are we going to get? we are going to get something like this. This is a 3D map for a continuous kernel density estimation function. So this 3D map is representing that there are 3 points of high density feature value. You must have already guessed by looking at this data that there are 3 clusters. But if you have used a wrong value of bandwidth or the standard deviation, then you might have got a large number of modes or peaks or a low number of modes or peaks. So this graph represents this information in contour forms. You can see that there are higher values over here and over here and over here. The green color is representing higher values, and as you move away from these peaks, the color is converted to black, which represents lower values. So once we have done this thing, the last step is to move all the points in the direction of the gradient so that we can know that which point correspond to which peak. So this is shown in an animation over here. You can see that all the red points corresponding to this peak are moving towards it. All the red points corresponding to this peak are moving in this direction, and all the red points corresponding to this peak are moving in this direction. So at the end, we are going to have 3 red points or 3 modes or 3 categories. So all the points lying over here, they are going to correspond to this category. I'm going to label this thing as category B. All these points are going to correspond to this category. I'm going to label this category as A, and all the points lying in this region, they are going to correspond to this category, which is category C. So we have categorized all data points into 3 distinct categories. You must be wondering that how this mean shift technique or algorithm can be implemented to segment out objects. We haven't done any segmentation yet. So in the next example, I'm going to do mean shift segmentation, which was the name of the topic. So consider this complex image which we want to segment out. Your brain can easily see that this is one region, this black region, it is one region. This green region is another region. This yellow region is the third region. Then we have a fourth red region. Then we have these light yellow regions. These regions will correspond to fifth region. Then we have these grayish regions. They will be sixth regions. And we also have this black region over here. This black region is going to correspond to this one. So these two regions are the same. And we have this white region over here as well. There is also this red region, but this red region is going to correspond to this red one. And this yellow region is going to correspond to this yellow region. And we also have this blue region as well. So you can easily categorize and you can easily segment out this whole image using color information. How we can implement segmentation using mean shift algorithm on this image. So the first thing is we need to decide that what feature values we are going to use. Just like your brain has used colors to segment out all the regions in this image, we are going to use color values as features. So if we use colors, we know that we can represent colors using 3 different primary numbers, that is the number corresponding to R, G, and B layer, that is red, green, and blue layer. So each data point, for example, this data point can be represented using three numbers. For example, this data point is corresponding to green color. If this image is an 8-bit image, then it might be represented by this value. For example, a low value of red color, a high value of green color, and a low value of blue color. So these 3 points might be representing this pixel over here. In the similar fashion, this point, which is a red point, might be represented by a high value of red color, for example 230, a low value of green color, for example 20, and a lower value of blue color, for example 30. So each pixel present in this image will be represented by three different values, and these three values are going to represent color. What if we use three-dimensional feature space, where one dimension is representing the red color, another dimension is representing the green, and the last dimension is representing a blue color. So we will have a three-dimensional feature space, and we can label or we can place all these pixels present in this image at some location in that three-dimensional feature space depending on the value of the color present at that pixel. For example, this red pixel is going to lie at 230th location in the red axis, 20th location in the green axis, and 30th location in the blue axis. So we can have x, y, and z coordinates for three-dimensional feature space, and this point is going to lie over here. So if we plot all the points in a three-dimensional feature space, it will look like something this. This dimension is representing red color, this dimension is representing green color, and this dimension is representing blue color. So you can see that points having 0 red in them, 0 green in them, and a high value of blue in them are located over here, and they are appearing as blue points. All the points having low value of red, low value of green, and low value of blue means that those points are black and they are being positioned over here. Similarly, red points are lying over here, green points are lying over here. They have low red values, low blue values, and high green values. And these points, they have high green values and mediocre blue values. So they are somewhere over here and they are appearing as yellow. So the next step would be to design a 3D kernel function. Because we have a 3D feature space, we need a 3D kernel function. And we'll need to apply that 3D kernel function onto each point so that we can get peaks in three-dimensional feature space. And those peaks are going to correspond to different modes present in our data. So the application of 3D kernel density function will generate 7 different peaks. So one peak is lying over here, another peak is lying over here, another peak is lying over here, the third one, this is the fourth one, this is the fifth one, sixth one, and seventh one. So at the end, when when we start moving all the points in the direction of the gradient, those points are going to move towards their corresponding peaks. And at the end, you can see that all the points have settled at one of these 7 peaks. So all the points lying over here, they will correspond to peak number 7. All the points lying over here, they are going to correspond to peak number 6. And similarly, all the points lying near to these peaks, they are going to arrive at those locations. So now all the points, all the pixels present in the image, they have been categorized into 7 different colors. One color is represented by this value, one color is represented by this value, and similarly 7 colors are represented by these values. These values are coming from this red, green, and blue axis. So what if we label all these pixels corresponding to peak number 1 with this value, all the pixels corresponding to peak number 2 with this value, all the pixels corresponding to peak number 3 with this value, and similarly all the pixels corresponding to their peak value with the value of these peaks. So what are we going to get? We are going to get something like this. So you can see that this is one region. All the pixels present in this region, they are colored or they are being represented by same color value. That is, it might be, for example, 10, 10, and 10. All the pixels present in this region, they are represented by another value. All the pixels present in this yellow region are being represented by another value, and we have a fourth region over here. A fifth region is this gray area which is appearing somewhere over here, over here, over here. So all these gray areas are region number 5, and this light yellow region is the sixth region, and this is the seventh region. So the whole image has been divided into 7 regions, and now we know that this green color is representing one region, yellow color is representing another region, and similarly all colors are representing a different region. You can use a different value of bandwidth to get different number of regions. Here you can see that we are not getting this white color. In original image, this was white, but these white pixels, they are corresponding to gray color. That is, they are moving in the gray colored peak. This is because we don't have a peak for white color, which means that we might be using a large value of bandwidth. So if we decrease the value of the bandwidth, we are going to have more number of peaks, and possibly we might have this white color as a different mode. So same is the case with this blue color, because if you remember in the original image this plus was written in blue color, but over here we don't have any blue peak, and these points are corresponding to gray or black peaks. Here are some other real life examples where you can use mean shift segmentation to segment out objects. You can see that in this real life image, mean shift segmentation can easily segment out this object from the hand. Here is another example where this complex real-life image has been segmented out using mean shift segmentation. So mean shift segmentation, it knows that this is one region, so it has colored this whole region with one color, that is this one. It has labeled this region with another color, so it is another region. You have a third region over here, a fourth region over here, a fifth one, and a sixth one, and a seventh one, and eighth one, maybe. So mean shift segmentation has easily divided this complex image into 8 different regions, and it has segmented out different portions very easily. Same is the case in this image. This one is a mean segmented image, whereas this one is the real image. So I hope that you have understood how mean shift segmentation or In the first step, mean shift algorithm works and how this mean shift algorithm can be used to segment out different regions of an image using, for example, color features. So here are the references for this lecture. Kindly feel free to contact me through a suitable communication medium if you have any queries.